Welcome to lecture 21 on the course Foundation of Mathematics. Under this lecture, we will understand the concept of image of a subsets under functions. So basically, when we have a function from a domain X to a domain Y, we have spoken about under function f, we have spoken about the image of a point, right? So if we have a point x in x, it moves to this y through this f and gets converted to f of x when it reaches to y. Okay, so now instead of talking about the image of one point, we talk about the image of a subset under this function. So obviously, by definition, this would mean that image of this subset is nothing but the set of all the images of elements of this set A. So for every subset of X, we have an image of a subset of that set under this function f. So we call it as the image of that set under f. Okay, so for this set, obviously the notation should be f of a. For this set A, we collect all the images of the elements of A and we call it as f of A, which is a subset of y. So the definition should follow in this way. So definition. Let f from x to y be a function. And A be a subset of x. Then we define image f of A. This is the notation for the image of this subset f of A under function f to be the subset so it's a subset of y and it is defined in this way f of A, so it's a set of all the elements in y which has a pre-image in A. So that is same as saying there exists A in A such that image of A such that AX has the such that image of A under F is Y. So basically, so this is a subset of Y. Basically, we are collecting all those elements of Y which has a pre-image in A, not in X. The other way of writing this same set would be set of all y in y such that y is equal to f of A for some A in A. So that means if you are collecting a point from f of A, it should have a pre-image in A. So in short, we can write this down also as a set of all image point, a set of all images of the elements of A. So that is simply writing it as f of x where x belongs to A. So in this way we collect all the images of the element of A. Now through this definition one can make some natural observations. So we put it in the form of remark. The first one, as we know that even an empty set is a subset of X. So for that empty set also we need to define its image. So what should be f of empty? By definition, it's a set of all the elements of Y such that there exists X in empty set such that f of x is equal to y. Okay, so there exist, but we know that from empty set we cannot produce any elements, and therefore there no such x exists such that f of x is equal to y, and therefore there is no such y in y such that it satisfies this condition, and therefore this has to be an empty set. So this is the first remark. Second thing, a very important thing, we can talk about a singleton set. Okay, what should be if A is a singleton x1, say it's a subset of x, say something like this, it contains only one element, then what you expect its image. So it is clear from the definition of a function that this x1 will map to a unique point in y, and it is given as f of x1, and it's not going to have two images, right? By the definition of the function, it's going to have one and only one image in y, and for sure it's going to have image because every point in x is mapped to some unique point in y, and therefore we cannot expect this set to be empty set, and we cannot expect this set to be a set consisting of more than one element. So this is a set consisting only the image of x1, so f of x1. So remember that, so if we have a set A as a singleton set x1, then its image set contain only its image of that particular point. Next observation that one can make through this definition, through this representation of f of a. So if x belongs to a, then we can immediately conclude that f of x has to be in f of a. But is the converse of this statement is true? We will answer this question shortly. That is, if f of x belongs to a, then does that imply that x has to come from a? Okay. So we will answer that question. Before that, let me take one more remark. A range of a function, we know that it's a subset of y, and it's a collection of all the pre-images of it's a collection of all the points of y which have a pre-images in x. So range of f also can be written as the image of certain subset of x. And what is that certain subset of x? Let's recall the definition of range of f. So it's a element in y such that there exists x in x such that I can write down f of x as y. So you are collecting all the points in y which has a pre-image in x itself, and therefore this has to be f of the whole domain, which is again a subset of x. Okay, x is a subset of x. So these are certain observation. Okay, now to prove that the converse of the third one is not true, we can produce a counter example. Okay, so the question is, if f from x to y, is a function and a is a subset of x such that f of x belongs to f of a, then from here can I say, is x compulsorily coming from a? Okay, that may not be true. You just look for the simple example. One simple example one can think of this, f from r to r, a constant map. Okay, say all the point maps to say some element 1 here. Okay, now I'll consider one proper subset of R. Say, suppose this is the proper subset of R. We know that its image is going to be a singleton set, that is 1, its image set, right? So even I can have some point not coming from this set, see this point, which is not coming from this set, but still it is mapped to 1, and therefore its image contained in the image set of this set A. So that's the whole idea. So consider the answer is no. Consider counter example is this: f from R to R defined by f of x is equal to 1 for each x in R. Okay, now let me take one proper subset of R. Let A be say 0 comma 2, close interval 0 comma 2, which is a subset of R. Now it is clear from the definition of this map, f of 0 comma 2 is nothing but a singleton one, because every point in 0 comma 2 will map to 1. Okay, now I'll take a point outside this. I'll take a point outside this interval. So let x be equal to say -1. Okay, now f of x is equal to 1, which is a part of a singleton 1, which is a nothing but f of 0 comma 2. Okay, but x does not belongs to 0 comma 2. So this is the counter example to show that if f of x belongs to say f of a, that really do not implies that x has to come from a. Okay, before we look into some properties of this image of a subset, we take one illustrative example to understand the whole idea of image of a subset. So example 1, consider a simple function defined by f of x is equal to x square. Okay, what I'll do is that I'll take some subset of R. So first I'll consider A to be say a finite set containing -1 and 1 as a subset of R. Now the question is, what is f of A? So again, you just since it's a finite set containing only two elements, obviously this image set will be non-empty. Okay, because every element in the set, every element in the domain is mapped to at least one, is mapped to a unique element. Okay, so therefore this set is going to be non-empty for sure, but you need to find explicitly what is this set. So what I'll do is that I'll take every element from this set. Since it's a finite, I can very easily find out where it is mapped to. F of -1 is mapped to -1 the whole square, which is nothing but 1, as well as f of 1 maps to 1 square, which is equal to 1. So both these elements maps to 1, and therefore you have something like this. Therefore, if I consider the image, image subset of this set -1 and 1 under F, it's going to be a singleton set 1. So therefore, F of A is nothing but a singleton 1. If I change this A, let me use some new notation, B to be a set 0 comma 2, closed interval 0 comma 2. Then also it is very clear, just your domain is fixed to 0 to 2. You need to see the image when x lies in this 0 to 2. So when x lies in this 0 and 2, you will see that x square is always positive, and since 2 is the maximum of 0 and 2, x square will take the maximum value 4, and therefore we say that x square belongs to 0 comma 4, which implies that for each x, f of x belongs to, for each x in 0 comma 2, f of x belongs to 0 comma 4, and therefore I can say that image of 0 comma 2 under f is nothing but closed interval 0 comma 4. Fine. Now if I change the set, say C, to -3 comma 4, this is a subset of R. You can in fact plot a graph you have a minus 3 this side and you have a 4 this side. Or in fact I'll take the other way around, minus 4 comma 3, because I just want to give an illustrative example. So minus 4 and 3. So corresponding to 3, x square is 9. So it's going to lie somewhere here. The point is going to lie somewhere here. And corresponding to minus 4, x square is 16. So the point is going to lie somewhere here on the graph. And so when you plot a graph, you'll see that this keeps on decreasing. It will become 0 when x is equal to 0. And so it covers this entire stretch of the y-axis when x moves from minus 4 to 3. And therefore the image of this set, that is minus 4 comma 3, is nothing but 0 comma 16. Okay, so you make a statement when x lies in between minus 4 and 3, x square is always greater than or equal to 0, no matter what. Now you just see what is the maximum distance of x from left of the 0 and from the right of the 0. This is 3 and this distance is 4. So you take the square of this, that's nothing but take the square of the maximum, that's nothing but 16, and therefore you see that x square belongs to 0 comma 16. That is same as saying f of x belongs to 0 comma 16. Although this is not a formal proof, you can produce a formal proof with this idea, and therefore I can say that f of c is nothing but the closed interval 0 comma 16. Okay, so now let's discuss some properties of image of a subset under function, some standard properties. Okay, so the first property, I'll call it as a theorem. So this is a comparison of two image set of for the two set in the domain. So let f from x to y be a function and a comma b are the subset of x. Okay, so if a is a subset of b, then as expected f of a has to be a subset of f of b. Okay, so let's prove this using the definition of a subset. So what I need to show is that it is given that a is a subset of b and both this has a subset of x. We need to show that f of a is a subset of f of b. So definitely I'll start with any element in f of a and I'll show using definition that it is an element of f of b. By the way, you have a picture something like this. This is your a is contained in b. So this is your a and this is b. And you need to show that if this is true, then f of a is also contained in f of b. As you can see that f of a and f of b are subsets of y. I'll start with, instead of so the standard way of using the notation would be take any y, not an x, y in f of a and show that it is in b. So let y belongs to f of a. What does this mean by definition? There exists a point x in A such that x is the pre-image of this f of this y. Okay, so therefore there exists x in A such that f of x is equal to y, or y is equal to f of x. Okay, now you know that A is a subset of B, so if x belongs to A, x also belongs to B. So since A is a subset of B, this implies that x also belongs to B. Okay, and so if x belongs to B, f of x will belong to f of B. That is same as saying y belongs to f of B. So in other words, you have produced a point, so you are actually going in a reverse way. So you have produced a point in B whose image is in f of b, and yeah, definitely its image is going to be in f of b, and this implies that y is in f of b. So since we have started with any point in f of a and proved that a point in that point lies in f of b, we have proved our claim. So therefore f of a is a subset of f of b. So this is one of the property. Next property talks about the union of two sets. So suppose this be a function, and suppose you have a and b as subsets of x, a and b of x. What can we talk about f of a union b? Will this function f preserves, will the union will be preserved to the function f? Okay, and that is true. F of a union b is same as f of a union f of b. Now again note that for any subset, its union also belongs to the same, will also have the same universal set. Okay, so this makes sense. Since a and b are subset of x, a union b is also a subset of x. So first thing, we need to make a statement that since a comma b is a subset of x, this implies that a union b is a subset of x, and therefore I can talk about its image. So I need to show this, that is f of a union b is nothing but f of a union f of b. So I'll prove this by showing that this f of a union b is a subset of f of a union f of b and vice versa. For this I'll see if I can make use of the above theorem. Okay, what I know is that A is a subset of A union B because A union B is a bigger set if I compare to A. So A is a subset of A union B, and therefore by the previous theorem f of A should be subset of f of A union B. This is the first statement. Now similarly also B is a subset of A union B, and therefore this says that f of B is a subset of f of A union B. Now you can see that this f of A and f of B lies in the same set f of A union B, and therefore by one of the properties of union of a set, uh, the union of these two sets f of A and f of B should also lie in the same set. Therefore from 1 and 2 I can say that f of A union f of B is a subset of f of A union f of B. So from here we have established one way, that is we have shown that f of this is contained in this. Now to show the other way around, that is f of A union B is contained in f of A union f of B, we use the definition. So let me start with any point in, okay, this would implies that there exists x in A union B by definition such that xx is the pre-image of y. So that is f of x is equal to y, or y is equal to f of x. Now x belongs to A union B, this would mean x belongs to A or x belongs to B, and therefore I will discuss this statement in two cases, and I'll show that both the cases lead to the fact that y is in f of A union f of B. So if, because there is a or, so if x belongs to A, this would implies that f of x, that is y, will belongs to f of A, which in turn contain in f of A union f of B. By the way, both these sets are the sets in y, and therefore I can compare f of a with f of a union f of b. This is the bigger set, and therefore f of a is contained in f of a union f of b. Okay. Similarly, if x belongs to b, also you can see that y, that is f of x, will be in f of b, which is again contained in f of a union f of b. Okay, and you can see that wherever that x may be lying, either in a or in b, f of x will always lie in f of a union f of b, and therefore I can conclude that f of x, that is y, belongs to f of a union f of b, which is enough to say that this shows that f of a union b is contained in f of a union f of b. I'll call this as double star, and therefore from star and double star we have f of a union b is equal to f of a union f of b. That's it. Okay. Now, unfortunately, the same statement do not hold for the intersection. In the intersection, we do not have f of a intersection b is equal to f of a intersection f of b. In fact, in general, only one way is true. Image of the intersection of two sets is contained in the intersection of images of those sets. So I'll mention that as a statement, and in fact we can produce a counter example wherein counter example function wherein the two sets are not equal. So theorem, so let f again be function, then for all subsets a and b of x, we have f of a intersection b is contained in f of a intersection f of b. The other way around is in general not true. So the proof for this is in fact can be generated through the definition of image subset under a function. So what I'll do is that I'll start with, okay, first thing, we know that for any subset A and B, the intersection also is a subset of the same set. Okay, so I'll make that statement as well. Let A comma B be a subset of X. This implies that A intersection B is a subset of X, and therefore this makes sense. So let me start with any element in f of A intersection B. Okay, so this would mean that there exists x in A intersection B such that y is equal to f of x. That is, x belongs to A and x belongs to B such that y is equal to f of x. Okay, so if I split this now, if I say that x belongs to A okay, and y is equal to f of x, then this would imply that y is in f of A. And again, if x belongs to B and y is equal to f of x, both will happen because there is an and. Then this would imply that y is in f of B, and from here we see that y belongs to f of A as well as f of B, and therefore y belongs to f of A intersection f of B. Okay, so this proves that f of A intersection B is contained in f of A intersection f of B. Now let's produce a counter example to show that the equality is not true. In fact, you can do it. Very simple example you can construct. Okay, let me do it over here. give an example of a function to show that f of a intersection b is not equal to f of a intersection f of b for a and b a subset of x. Now this the equality do not attain only because the converse way is not, that is f of a intersection f of b is not contained in f of a intersection b. So you need to produce an example wherein that do not hold. Okay. So you can think of again a simple example, maybe a constant example will work. So let f from R to R defined by f of x is equal to 1. Okay, in fact you can take any other constant instead of 1. Okay, let me take a to be equal to say minus infinity, open interval minus infinity comma 0, that is the left part, and b to be 0 comma infinity. So in fact you see that a intersection b from here is empty, and therefore this implies that f of a intersection b is empty, right? But what about f of a intersection f of b? This is nothing but f of a, since all the elements of this maps to 1, this is going to be a singleton 1, and this is also going to be singleton 1, so therefore the intersection is 1. So you can see that this f of a intersection b is totally contained in f of a intersection f of b, and therefore since it's not a subset, it is okay, it is not a they are not equal. Okay, since this is totally contained in this set, they are equal. So therefore you have f of a intersection b is contained in what notation we use over here, we call this as, is a proper subset of f of a intersection f of b, and therefore they will never be equal. This shows that will never be same as f of a intersection f of b. In fact, you don't look for an example wherein f of a intersection f of b is totally contained in f of a intersection b. That will never happen, because the other way around is always true. That is a proper subset of f of a intersection b. Okay. Yeah. So now, under what condition this has to be equal, or what is the condition that we need to impose on the function f so that the equality is attained? So that's one of the interesting, and see from this example it is very clear, or you can get the picture of the condition that should be imposed on a function so that we get the equality. We want a intersection b to be mapped to f of a intersection f of b. So this will happen provided there is a one-to-one correspondence between each of the points of x and y, or each of the points of a intersection b and the other side, that is f of a intersection f of b. That is same as saying one-to-one, as in, you may have a point in the codomain which do not have a pre-image. Okay, but there should be one-one correspondence. So that suggests that the function has to be one-one, then only the equality will be attained. So that is the next property statement. A function f from x to y is 1 1 if and only if, or in fact injective, or if and only if f of a intersection b is equal to f of a intersection f of b. This is in fact an if and only if condition, a biconditional statement, and this holds for any subset of x, holds for all subsets of a and b of x. So first we will assume that the function is 1 1, and we will show that for any subsets a and b of x this is always true. In fact, we need to show only the that f of a intersection f of b is contained in f of a intersection b, because the other way around is always true no matter whether the function is 1 1 or not. So proof has a two part, the direct implication, in which we consider 1 1. Okay, and we need to show that this is true. So basically we need to show only one part, f of a intersection f of b is contained in f of a intersection f of b. The reason is, as we have already proved, f of a intersection b is contained in f of a intersection f of b. Fine? Okay. So I'll start with any element over here, and I'll show that it belongs to f of a intersection b. So let y be an element in f of a intersection f of b. By definition of intersection, this means that y is in f of a as well as in f of b. And what this would mean? This would mean that there exists x1 in a and say x2 in b such that they have the same image. For y belongs to f of a, x1 acts as the pre-image, so therefore f of x1 is equal to y, which is same as f of x2. So x2 acts as the pre-image from b for y. Okay, so therefore what we have, thus we have f of x1 is equal to f of x2, and this implies that this x1 and x2 that are coming from a and b have to be same. Okay, because the function is injective. Okay, so now is this enough to say that x1 and x2, or to say that x1 is coming from a intersection b such that f of x1 is equal to y? That implies that y is in f of a intersection b. So therefore there exists a point x1 and in fact x2 in a as well as in b, because x2 is in b, and x1 which is equal to x2 in b, such that f of x1 is equal to y is equal to f of x2, which means that there is a point x1. I'll talk only about x1 and x1 belongs to a and b, so that is same as x1 belongs to a intersection b, such that f of x1 is equal to y. So this is how we are trying to deduce to get what we require. That same as saying, this is same as saying for given any y from where we have started, there is a point in a intersection b such that f of x1 is equal to that y, and therefore this is same as saying f of x1 belongs to f of a intersection b, that is y belongs to f of a intersection b. That's enough to say that f of a intersection f of b is a subset of, because we have started with any arbitrary element y. Okay, and hence we are done. We don't have to prove the other way around, that is already always true no matter whether the function is 1 1 or not. let's get into the converse part of this. So conversely, let f of a intersection b is equal to f of a intersection f of b for any a and b subset of x. So you need to use this fact that this is true for any subset of x to show that f is 1 1. Okay. So what I'll do is that I'll apply the definition to show that the function is 1 1. So I'll take two distinct points in the domain of f and I'll show that they have a distinct image. Consider x1 comma x2 is in x such that x1 is not equal to x2. Now I'll make use of this fact. So here I'll produce my subsets A and B, and for that I'm going to use the given fact. So let me construct the set A as a singleton x1 and B as a singleton x2. Okay, now both this A and B are a subset of X. Okay, and therefore uh, f of A intersection B has to be same as f of A intersection f of B. Okay, but what you know about f of A intersection B? As x1 is not equal to x2, f of A intersection B or A intersection B is nothing but an empty set. So this is an empty set as A intersection B is empty. That's clear because x1 is not equal to x2, therefore there is no common element in A and B, and therefore this is empty. So this implies from star that f of A intersection f of B is empty. That is, there is no common element in f of A and f of B. In f of A and f of B, because A is a singleton set, this is nothing but, by definition, this is what we have. Okay, by definition this has to be same as f of x1, okay, intersection f of x2, by the definition of the image subset, and this is one of the remarks that we have given. This set is nothing but the set containing f of x1. Okay, so this is non-empty. That means since it has only one element and they are empty, they are disjoint, means those elements are not same. So therefore f of x1 is not equal to f of x2. And this is enough to say that the given function, because we have started with any two x1 and x2 distinct x1 and x2, and we have shown that their image is distinct. We make use of the fact that this is true for the f of A intersection B is equal to f of A intersection f of B holds for any subset of x, and so we produce a subset of x and we apply the result. Sorry. So in general, this also acts as the definition for the one-oneness of the function. A function, I would request my student to go through the same section on the given principal text and solve the exercise mentioned in the same section. Thank you for watching this video and have a nice day ahead.